So, we are discussing the axiomatic system FC for the first order logic. Then along with the axioms we had now two inference rules, unlike your PC. PC had only one. The same we have kept as MP plus another for universal generalization, and in the axioms we have all the three axioms of PC plus there are some more. So, two more for the quantifier and two more for the equality predicates, right. So, that is how we started. Then we proved two theorems, monotonicity and deduction theorem. Then just like your PC, you can also formulate reductio ad absurdum, the same formulation, the same proof, right, because there is nothing much there. Anyway, just we tell them what it is. So, you have one consequence to be proved, sigma entails x. In that case what you do is add not x as a new premise and then show that sigma union not x is inconsistent, right, and this process is reversible. If sigma union not x is inconsistent, then you say that sigma entails x, right. This is your reductio ad absurdum basically. Then let us apply all those meta theorems in proving some of the theorems. In fact, we will not prove them as theorems, because we are not going to give a proof of that directly. So, that means we will show that it is provable, fine. So, which means you take some formula and then maybe using some reductio ad absurdum or deduction theorem you transfer it to some other consequence, then give a proof of the consequence. Because of the meta theorems, the original formula is provable as a theorem, right, that will be the approach. So, let us see example 1, which is really propositional, right. X implies not y implies not of x implies y, there is no quantifier involved directly, though they are now from formulas from FC, not propositions necessarily, right. Even for any formulas you have the reductio ad absurdum and the deduction theorem, so you can apply and get it done, fine. One easy way to look at it is, see, you have the law of contraposition, right. So, if you can prove x implies y, then it is done, right, if you use law of contraposition. Even without using it you can do, because you have RAA, right. So, let us try that way. Say first is by deduction theorem, it is enough to prove x entails not y implies not of x implies y, fine. Then you say again another application of deduction theorem says x not y entails not of x implies y, right. Then with reductio ad absurdum you show x not y and x implies y, that is inconsistent, okay. Then you say again by reductio ad absurdum x implies y entails y, right. You now choose this one as your formula, which has come from the consequence. If you look from this to this, you will see easily not y is added and that is inconsistent, right, and there is nothing to prove here, it is MP, right, for which you can give a proof, say x implies y, therefore y, or just give this is a premise, this is a premise, this is modus ponens, that is all. Is it clear? So, this contraposition has been proved inside it. This is not new to you, the same technique of PC, that is what we have done, okay. Is it clear? We proceed to next example. So, here we have for each x equal to f of y implies qx, then we show that qf of y, again deduction theorem might be handy. So, let us say by deduction theorem we just show for each x equal to f of y implies qx, entails q f of y. Right. Now, this can be shown, it is easy to show here. Just what you have to do is take a suitable instantiation of this universally quantified variable. Right. So, we start with our premise for each x equal to f of y implies q of x, that is a premise. Okay. Next, one axiom for instantiation. So, x equal to f of y implies q x implies f of y equal to f of y implies q of f of y, right. Is that okay? For each x, x implies x by t, is that right? So, this gives you which axiom? F of. Next, use MP to get f of y equal to f of y implies q f of y. Next, use another axiom, equality axiom, and then mode exponents. Okay. So, I leave it there. This is which axiom again, just to remember them. 3 were from PC, 2 were from universal. Next one, right, A6, and then an application of MP finishes it. Clear? So, let us try next example. For each x, x implies y implies not for each x not x, which is really your there is x x, and you given in that form, that is also fine. You can use the definitions and reduce it to this one. Finally, this is to be proved. So, this will say for each x, x implies y implies there is x x implies there is x y, right. So, again we use deduction theorem. This says for each x, x implies y entails not for each x not x implies not for each x not y. Here itself you can use contraposition, right. By contraposition it is enough, but contraposition we can't use here, it has to be used inside the proof. Again only meta theorems we can use outside the proofs. So, then let us use again deduction theorem, which says for each x, x implies y and not for each x not x entails not for each x not y. Okay. Next, use array, because this not will be difficult to use as a premise, fine. So, we take for each x, x implies y not for each x not x along with for each x not y is inconsistent. Okay. Once more use array to take that negation to the other side. So, we say for each x, x implies y, for each x not y entails for each x not x. Now, you see contraposition has been used through array. We should be able to prove this. It does not look to be more simplified than this. So, let us try a proof for each x, x implies y premise, for each x not y premise. Next, well, we can just say x implies y, and similarly, in fact, it did not go in one stage, axioms have to be used and then MP has to be used, it has to be brought, right. So, what we do is for each x, x implies y implies x implies y, that is axiom 4. Okay. Then MP, which will give you x implies y. Two steps will be required, right. So, similarly, another 2 steps will give you not y. Okay. There you will be using PC. So, this comes from again same way, you can fill it up. Next 7 will be not x, right. Then over universally generalize for each x not x, is that okay. So, 8th line will be for each x not x, huge. All that you have to see is x is not free in the premises, which is not, in no premise it is free. So, even used thus far whatever it is, x is free, x is not free in all the premises used till now. So, for each x not x, clear. Now, next one. So, by deduction theorem we have not for each x, x implies y entails for each x not of x implies y. Right. Now, some mental block, how to use this not. Well, you use array, transfer it to the other side, see what happens. So, this gives by array not for each x, x implies y, and then not of this, this is inconsistent, right. Then again array which gives not for each x not x implies y entails for each x, x implies y, fine. Okay. Then use deduction theorem which says not for each x not of x implies y for each x, x entails y. Clear. Again this not is again with for each. So, you have to take it inside, you can take not y also. So, R A will give for each x, x not y entails for each x not of x implies y, twice. I have used it twice, right. Not y comes here which is inconsistent, right. Then I take it to the other side by array again. So, for each x, x not y entails this, clear. Now, probably this will be easier to show. So, one you have for each x, x, then second or rather third line use axiom 4 for each x, x implies x. Next use modus ponens to get x. Both will be used. Is that okay? Second line will be for each x, x implies x, that is your axiom 4. Then modus ponens on these two to get x. So, after you get x, you have not y premise. Now, what is your target? for each x not of x implies y. So this can be obtained by universal generalization UG. So you want to get this, now that is propositional, which is our example 1, right. So use example 1 as a theorem, previously proved theorem, then used modus ponens with x, you get not y implies not of x implies y, again modus ponens with not y, right. So you get not of x implies y.
What if we didn't know example
1? You prove it.
Sir, exam however we
You will have to prove it. No? So once you see that x and not y gives not of x implies y, right. So that is really a PC theorem, it is a PC consequence. So you can always bluff it is PC and then continue fine, but then it need not be a theorem, so better prove it. Is that okay? But it can be done some other way, your bluff might be correct. See, there is one nice thing, how to prove the trigonometrical identities. There is a nice algorithm to prove them, which you never know in our high schools, otherwise we would have scored 100%. See, the algorithm is, suppose there is a trigonometrical identity, left side equal to right side, you know it is an identity, right, it is given in the book, so it must be identity. So what you do is, start left side writing whatever identity you know, go on applying it, and here from the bottom you start from the right side, whatever you know go on filling it, leave it there right, and it is not wrong, right, whatever you get in between, that is correct identity. Is that okay? So it depends on how much you have to spare in the paper. Continue. So the same way you can leave it here, you know that x not y should give you not of x implies y semantically, because x not y both are there, it is equivalent to x and not y, and not of x implies y is equivalent to x and not y. So it should be provable because it is complete system, PC is complete, so there is a proof of it, right. But what the proof exactly is you do not know, so leave it, theorem, PC theorem but better to prove it, and we have proved in example 1, okay. So that means it will give after some steps, let me write it some 8 star, I do not know whether it is 8th or 9th. So there you get not of x implies y, then we use UG, so that gives you for each x not of x implies y. Then let us see this. See, with not of a equal to b it is not easy to get, right. So use array from the beginning. So by array we try to show PA for each x, Px implies Qx, for each x Rx implies not Qx, and Rb and A equal to B is inconsistent. Now with A equal to B it should be possible, right, but there are constants A and B, so you do not know which one we will instantiate. If you instantiate wrongly you may not get that, fine. So we do not know exactly whether we will get not PA or not RB or even not QA or not QB, something which will bring the inconsistency, that is not very clear now. That always happens whenever there are instantiations. Earlier what happened, earlier cases of array there was no instantiation, so they are almost propositional, everything should be possible, but now there is instantiation and A equal to B, so I do not know which one I will be able to derive, not P I will be able to derive or not RB which will contradict, or QA not QA, QB not QB, I do not know which one. So let us keep it in this form and continue towards deriving inconsistency, right. Okay. Now I start from say for each x Px implies Qx. This is a premise. So, third line, second line I want to use my PA, right. Since I want to use my PA, I want to instantiate it. So, write in the second line, for each x Px implies Qx implies PA implies QA, right. It is axiom 4, A4. Then use modus ponens to get in the third line PA implies QA, right. So, A4 and modus ponens. Okay. Then I can use PA as the premise and get my modus ponens QA, right. But here I have R A not Qx. Anyway, I can use R A still because I have already QA, or for R B I can use B also, any one of the instantiations will do. Okay. Which one will go, A or B? With B, okay, fine. Then sixth one, introduce the premise for each x Rx implies not Qx. Then again eighth line will be Rb implies not Qb. Okay. Then you have ninth line as Rb, that is a premise. So, seventh line I have left it, that is axiom 4. So, you should have justification here as A4 and MP. Right? You have to fill it up, do not leave it like this. Then ninth is RB, so I get in the 10th line not QB by modus ponens. Fine. Then A equal to B has to be used. So, 11th line is A equal to B premise. 12th we have already QA, we have not QB. A equal to B, that should give the contradiction, right, that should bring in inconsistency. So, you have to use A7, A equal to B implies QA implies QB. X S equal to T, X X by S, X X by T. So, our X is QX. Fine, this is A7. Then modus ponens, so that gives QA implies QB, and we have already QA. QA is which line? 5th line. So, we just have QB. That is the end of the proof, right. You have to write a line, where is the inconsistency, right. So, inconsistency is proved due to formulas in lines not QB is in 10 and 14. Clear? So, it is easy now how the proofs will be going. So, the next concern will be whether this system really captures FC or not, right. It does capture, and we will not do the proof now. Proof again follows the same line as that of PC to PL, right. It is sound, it is easy to see, because all the inference rules are the valid consequences in FL, and all the axioms are really valid formulas in FL. Therefore, it is sound by induction. Okay. So, soundness is easy, completeness will be a bit difficult, because here you have to instantiate with all the terms. So, So, there is potentially infinite number of terms. So, for all instances you have to consider the formulas. Whenever there is some for each x, you have to really consider x substituted by all possible terms. All those formulas have to be extended in order to get one maximally consistent set, because that is our approach, to go to one maximally consistent set. So, to get that you have to really add all these instantiations, that makes it difficult, but then it can be done, because all of them are countable. So, they can be enumerated, the same procedure still can be used. Okay. So, we will not prove that, but we will mention. So, Fc is adequate to Fl. So, which really means you have two results, soundness and completeness. So, soundness you can say sigma entails in Fc x, then sigma semantically entails x in Fl, that is your soundness, and completeness is the converse of it. If sigma semantically entails in Fl x, then sigma entails in Fc x for any set of formulas sigma and any formula x, which you can write also with reductio ad absurdum in a different way, right. Once you show that it is adequate, you can prove something else, like can you generate all the theorems in Fl, all the valid formulas in Fl. Suppose first order logic is there, you know what are the formulas, you have the laws, but they are only the basic laws. Then there are so many others, infinitely many valid formulas are there. Can you generate all the valid formulas by using the laws? There is no completeness there. We are in semantic domain now. Well, since Fc is complete, it is enough to say by using the axioms and the rules of inference of Fc, can you generate all the valid formulas? Yes, because that is the definition of a theorem, definition of a proof. So, what you have to do is just feed all these things to a machine and program, write a program just to go on generating by following the rules, whatever it is, right. We are not asking it to prove a particular theorem, we are just asking it to go on generating by all possible theorems, right. So, it generates one by one, it gives you, right. So, that means the set of all theorems of Fc is recursively enumerable. There is a program to generate all these things, it is an output of a Turing machine, right. So, it is recursively enumerable. Since it captures all the valid formulas in Fl, so all the valid formulas in Fl, set of all that is also recursively enumerable, right. There is a program to generate all the valid formulas in Fl. The program is just programming of PC, implementation of PC, Fc, right. Is it clear? So, it is the next strong question we would ask, because it does not say when you will get your theorem, when you will get your valid formula to be proved, it just goes on generating on its own way, the way you have written the algorithm, right. But problem is, suppose you want to have a proof of something like this, right. That is a targeted one, you did not have any target till now, you just say go on generating all the valid formulas. Now, you say whether this formula is valid or not, give a particular one, that algorithm may not work, right. If it is, then it will work, right. So, that is the problem. See, suppose you know that something, some formula is valid, now your algorithm generates all the valid formulas. So, at some finite time it will be generated, and once it is generated it stops there, you can write another module on it, right, use that as a module, and once this is generated stop there, fine. So, it stops, it gives you yes, I have got a proof of it. So, that means if your conjecture is true, you get a proof of it. If it is false, no idea, it may not stop at all, it can run on infinitely, right. So, that is the idea of recursively enumerability, fine. If there is a targeted theorem to be proved, we do not know when we will get the proof, but we will get if it is a theorem. If it is not a theorem, it does not say anything, the algorithm need not terminate, fine. So, it is one side of our strong question, that given any formula, can you decide whether it has a proof or it does not have a proof, it only answers it partially, right. And the undecidability theorem for the first order logic says that the answer to the next question is negative, right. It is not decidable at all, it is recursively enumerable, but not decidable, means given some valid formula, you do not know whether it is a theorem or not. Once it is a theorem, you have a proof of it. So, once you have the undecidability result, you may say this recursive enumerability is a semi decidability result rather, because one part of it is the decidable, the other part is not decidable, that is why they are also called semi decidable problems. So, it is giving some more information to recursive enumerability, it is recursively enumerable, but not decidable, they are called semi decidable, right. So, undecidable we have not yet proved, we will see that once time comes, okay. But recursive enumerability it gives, that is all. What about your Habermas interpretations, for example? Suppose you do not use FC, you just go to the Habermas expansions, what happens there? You are given with one formula, FL formula, then you compute its Habermas expansion, right. Now, it is potentially infinite set, but infinite set of propositions, okay. Now, suppose it is unsatisfiable, now we leave the question of validity, because by duality it is enough to consider unsatisfiability. Now, suppose the formula given is unsatisfiable, then that means its Habermas expansion is unsatisfiable. Once it is unsatisfiable, by compactness theorem for propositional logic, there is a finite set which is unsatisfiable, right. So, now let us write an algorithm how to prove unsatisfiability from the Habermas expansion. We know there is a finite subset. So, start first one, is it unsatisfiable? Yes, stop there. If not, take the second one, ask the same question, is it unsatisfiable? If unsatisfiable, stop, otherwise add the third one, continue. If it is really unsatisfiable, it will stop somewhere, and that is one finite set you have got which is unsatisfiable. Compactness theorem guarantees that there is one finite subset once it is unsatisfiable, right. That is why the algorithm will terminate, is that right? But if it is satisfiable, again algorithm will not terminate, it will not be able to show that it is not unsatisfiable, right. Again the same thing is coming there, unsatisfiable sentences or unsatisfiable formulas in FL are recursively enumerable, okay. So, you can get the same result from the Habermas expansions also, but it does not say anything about the other side, undecidability, fine. So, for that you need some more results, like you start with a Turing machine, for example. Now, any Turing machine, its operation you can simulate by one first order sentence. So, let us say first order sentences, just the way we are translating some natural language arguments, right. What you do there, say all horses are animals, therefore, legs of horses are legs of animals. So, in this argument what you do is you take anybody is a horse Hx, anybody is an animal Ax, go on symbolizing it. So, you get one consequence in first order logic with your translation of those English sentences or English phrases to predicates, and similarly definite descriptions to functions and so on, okay. With that you do the translation. Now, suppose it is a Turing machine, then you have to see what are its fundamental propositions there or fundamental predicates. So, one is a Turing machine can go to the right, come to the left and so on, right. So, suppose you number the taps 1, 2, 3, 4 and so on, start from the finite tab, left side cut, right side only it is extended, not both the sides, that always can be done, okay. Starting from there, even if you take both the sides you can again manage with negative integers, right, starting from 0. So, let us say 1 to infinity. Now, what you do, if it is in some particular place, okay, then you say where the Turing machine is. So, you say W 5 means now it is scanning the 5th square. Okay. Next what you do, if it is just 5th square and some transition is applicable which says that go to the right by reading this symbol being in this state, right. So, now you have to say what is the state of the machine, what symbol it is scanning. So, it is in W and it is scanning so and so symbol. So, for each symbol you have a predicate S of something, what is being scanned, in which state is it, so you write T of something. So, T of that, now you say W of this, S of this, T of this, implies if there is a transition with that thing. So, you have to introduce a predicate if the transition is such and such, then action of the machine means after the next step the machine will be in this configuration, right. So, it will have this state, it will be scanning this square and so on. So, this can be again represented by the predicates, fine. So, each step of the Turing machine can be represented by a predicate, now by a formula. If such and such predicates satisfied, then such and such predicates are satisfied, right. That is how you will be formalizing the whole Turing machine now. Once the Turing machine its functions are given, you can just formalize, get a consequence. Now, you ask the question whether this Turing machine will halt or not. So, that means the halting state you have to translate now, right. So, it is in particular state H, that is again another predicate with H as the argument. So, halting of a Turing machine can be translated, therefore, you have a consequence, this Turing machine entails halting states, right. So, this translation is done now. Once it is done, that means halting problem for Turing machines is translated as a consequence, okay. But halting problem is undecidable. So, consequences will be undecidable, right. So, particularly that consequence, that set of consequences what you get from the Turing machines will always be undecidable, fine. So, first order logic is undecidable. In fact, this is the main thing why Turing started his Turing machines, to prove that first order logic is undecidable. That is how we got the computers now, it came from logic. Okay, so, that is the undecidability result of first order logic. There is another way of doing it, like you may be using so many predicates and other things for translating the Turing machines, you do not need so much, you may need only one binary predicate. If there exists a binary predicate in your language, first order logic language, it is enough to give you undecidability result. In contrast, if you have a language where only the monadic predicates are there, then it is not undecidable, it is decidable. For example, if you have all your consequences of this type, where you look at the predicates, there is one predicate P which is unary, another predicate Q which is also unary, another predicate R which is also unary, right. All these are unary predicates. So, suppose you get all consequences which use only unary predicates, no function symbols, right. That is your Aristotelian logic, monadic logic of Aristotle, like your Aristotelian sentences, no, all men are mortal, Socrates is a man, therefore Socrates is mortal, and all those sentences, they are all monadic first order logic sentences. Every predicate there is unary, it is also called monadic, unary or monadic, similarly binary or dyadic, there are some different languages. So, now what happens, if that is so, then it is decidable, but if there is at least one binary predicate or one function symbol, then it will not be decidable, fine. See, its trace can be there in the Habermas expansions. In the Habermas expansion, if you have one function symbol f, then you get one infinite domain. So, trace is found there, that probably that will be undecidable, that can be proved to be undecidable if there is at least one function symbol, or there is at least one binary predicate, then also you can show that it is undecidable. Okay. We are not proving that strong result also, but monadic predicates if the language only concerns monadic predicates or unary predicates, it is decidable. How do you show it? How do you show that if it is only monadic predicates, then it is decidable? FC arguments do not show it, right? FC says it is recursively enumerable, fine. What about undecidability or decidability? Hurwand expansion will be finite, right? There is no function symbol, is it not? Suppose like this, you have A, there is a constant, B, there is another constant, okay? So you make the Hurwand expansion. What about the equality predicate? It is binary, that will create problem. So in Aristotelian logic, equality predicate is also not there, right? So there is no problem. You get only a finite number of constants maximum in any consequence. So you have a domain consisting of those constants only. So in that domain you do it, transfer to Hurwand expansion, that is a finite set, so it is decidable, easy from the Hurwand expansions, right. Also the algorithm was given by Aristotle himself, there is another way of doing it, anyway we do not need it now, right. So this is the story about decidability results. So with this we stop our discussion of FC, we go to another proof method, okay. So what is our next proof method to discuss? Analytic tabula, right. That is what we have not yet discussed. So we have propositional analytic tabula, and now we want first order analytic tabula. So again it is an extension of propositional analytic tabula, all the connective rules are there, whatever we had earlier. Now we need not confine ourselves to implies for all, everything can be tackled there at a time, okay. Just like your connectives, all the connectives, even top bottom symbols were there in PT. So to extend it, we need some more rules to for the first order logic specific to it. So one is your for each rule, okay. This says for each x you can derive x by t, but then we add something else. So which says that the same thing can again be used, because with this one instantiation you may not be able to prove it, you may need some more instantiations, okay. In practice when we use it, we will not write this, but we will remember, we will reuse it. In contrast, if you have there exists, you can instantiate only once, after that you cannot use, fine. So we will have there is rule which says there is x, so get x by t, it is not repeated, you can't use it once more, right. But what is this term t? Now suppose you have already PC in the premises, you can't write again C, right. In some context in mathematics you are doing some problem, so you say there exists one number between 0 and 1 having such and such property, you say let that be alpha. Now again you find there exists another number within 0 and 1 having some other property, say you can't say let alpha be that, right. It may not be, it can be some other thing, okay. So that is what exactly done. This t should be a new term to the branch, to the path, whole path from the root to that place where it is being applied. It need not be new to the whole tabula till now generated, because all the tabulas are generated only path wise, depth wise. We are doing it breadth wise because of our convenience. By definition tabula is only depth wise, so it concerns only through the path, nowhere else. Then it is closed, we go to the next path, that is the way it is being implemented. So what we do, we say that t is new to the path, new term in the path. We will again say what is the meaning of this new. Right now we will remember this t means it is a constant, let us say it is a constant, right, it is a new constant, that will simplify it. It will need some experience to go for a generalization where you can use terms also, not only constants, any closed terms, any other terms even you can use. We will see that there are some other constants, we will see slowly. So, let us think of this t as a new constant for the time being, fine. Similarly, we will have rules for not for all, that will say not for each x, you can get not x by t, again t new, it is really existential, right. Not for each is really there exists not x. So, we will not write it is equivalent to there exists not x, therefore this, no, tabular rule is tabular rule. So, it will proceed this way. Then we have not there is, which says not there is x from which you get not x by t for any term t, and also repetition of the rule, repetition of the formula, it can be used once more. So, these two are really universal rules, these two are existential rules. Okay. And there are two more for the equality. So, in equality you have reflexive property of equality, which says anywhere you can add t equal to t, just as in resolution, right, it is like an axiom, anywhere you can add it. And there is substitutivity, which says if you have x, okay, let us start from equality, s equal to t, x by s, then infer s x by t. Fine. So, here it needs 2, just like your MPs. If both the things occur in the path, then you can extend the path by adding x by t, right. So, these are all the rules, extra rules for FT comparing with PT. Then the same way we will be proceeding as in PT, extend the tabula pathwise, then once you get negation and that formula itself both in the path, close the path, right. If the whole tabula is closed, then the formulas introduced at the root are inconsistent, the set of all those formulas is inconsistent. So, we are proving only inconsistency, nothing else. Then to prove sigma entails W, we show sigma union not W is inconsistent, RA is a definition now, right.